The final day of dealing with electric potential, voltage, potential difference, or just potential. So many names. And we are in the midst of going through the various arrangements of charge that we looked at in chapters 22 and 23 using Coulomb and Gauss to find the electric field, and now we are going back through them to look at the potential for each of those arrangements. And the line was an arrangement of charge that we were unable to deal with Coulomb's law, but then with Gauss's law we could, as long as we assumed that the field was uniform. That is, we or not uniform, but we didn't deal with the fringing at the edges, so we stayed towards the middle of the line. We did come up with the electric field from a line of charge. And now we'd like to deal with the voltage. The results are not going to be pretty. And the reason we are going through this is that it's not that you should memorize the results. In fact, I would encourage you not to, but that you should be able to go through the process of developing the results. And it will be asked of you. So here we have this line. I would like to know the potential here above the middle of the line, a distance d off of the line, and the idea would be to break this into little infinitesimals of charge, each one giving rise to an infinitesimal of voltage, dV, and then we'll add up all those infinitesimals of voltage to get the voltage at this point, and it's going to be a continuous summation. So I'm going to start by cutting the line in half, and I'm going to just do continuous summation for half of the line, and then I'll double the result that I get. And so I've got a little infinitesimal of charge that is x off the line, and that dq that you have there is actually equal to the linear charge density times dx, the little infinitesimal of distance that I have there. And the dV would be 1 over 4 pi epsilon dq over r. And r is going to be this Pythagorean addition of x and d that you have here. So and I'm going to evaluate that from 0 to L over 2 and then double the result to get the voltage. I'm going to do this continuous summation of all of those. Actually, evaluating this integral is quite tricky. I got several members of the math department to work on it. It turns out you do a very complicated trig substitution, and then it ends up being that the result is a natural logarithm. That I evaluate the natural logarithm at 0, and I get the natural logarithm of d, and I evaluate the natural logarithm at L over 2, and I get the natural logarithm of this complicated thing here. To subtract natural logarithms, we can make it a little bit prettier by dividing this term by d, as you see here. So there is the result. I would not expect you to hold on to that, but the setting up of this integral is vital, that you would be able to reproduce that. Next we go on to a disk of charge and finding the potential at a point D above the center on the axis of the disk. You say, well, whoa, wait a minute, Mr. Houghton, what about a ring of charge? We did the field from a ring of charge back in chapters 22 and 23. Yeah, but I say that a ring of charge is boring. And I'm going to ask you on your worksheet to explain why it's boring. And then we'll talk about it in class if you want to talk about it. But here, the choice I have made is to cut the disk into rings of charge, each one having this charge dq on it, and then I'm going to add up all of the dq's from the inside out to get the voltage. So it looks like this, that dV is going to be 1 over 4 pi epsilon dq over r. But the dq is going to be equal to the circumference of this ring, 2 pi r, times the thickness of the ring, dr. There's the area of the ring, and if I multiply that by the surface charge density, then I have the dq. And I hope you can convince yourself that that is correct. And this distance that it is away from the point we're interested in, again, is going to be that Pythagorean addition of these two distances. And I would evaluate that, the continuous summation from the inside to the outside. This one I can evaluate the integral because I've got that r up top as well as down here. Last time we didn't have the r in the numerator, but I could let u equal to the argument of the radical, and then du would be equal to 2r dr, and I've already got that 2r dr, and so I have I've got d sigma pi du over u to the 1/2, or times u to the minus 1/2, and so when you evaluate that integral, it's going to become u to the positive 1/2, and then you're going to have to put a 2 out front, and so this that 2 out front goes with the 4 to get you down to a 2 here, and of course the pi's take care of one another, and you get this result. Substituting 0 in for r, and you get this d, and substituting capital R in for r, and you get this expression here. So again, not so pretty that I would expect you to remember it, but the process of getting to it, I expect you to have absorbed completely. Okay, we're done with looking at potentials from various arrangements of charge. Now I want to deal with, again, the expression for potential or voltage as a function of the electric field strength. And we pause briefly while you say, oh yes, I know that, and what you know is that it is equal to the negative of the integral of the dot product of the field strength and the path that you have followed. Well, if potential is equal to the negative of the integral, then what is the field strength as a function of the potential? And what you want to do is take the anti-integral of both sides. That is, to differentiate both sides of this thing with respect to ds. And you get this expression, except we have funny d's here. That what these are called are partial differentials. That we have taken the partial derivative of v with respect to s. What does that mean? It doesn't have to mean anything at all to you. That if you just go ahead and take the regular old derivative of v with respect to s, the results you get will be exactly the results you want to get. So don't freak out over these weird new d's. Just deal with it like they look like regular d's. But let's talk a little bit about what's going on. The problem is that v is not just a function of where you are. It is also a function of how much charge. So v is a function of more than one variable, and you're only looking how it varies with respect to one of them. And that's what a partial derivative is all about, that something is a function of multiple variables, and you're only taking the derivative with respect to one of them. For example, in general, let's let f be a general function that is a function of x and t, if you like, position and time. And I want to take the partial derivative with respect to time. Well, here is what f might look like. It is a function of both your x and of your t value, and it's this wonderful membrane, this wonderful sheet going through the phase space here, that If you want to take the derivative of this function, which varies both with x and with t, and you only want to look at how it varies with time, what you need to do is to choose an x value and make sure that it does not change. So I'll choose to have x equal to -1. And then what I'm going to do is look at how t varies where x does not vary. And so what I'm going to do is to go along this slice through the sheet, and that is the values I'm going to get for df dt is going to be this function. That if I had chosen a different constant value for x, suppose I'd chosen 0, then I would be running along this sheet here. And you would have a different value for df dt because you had changed what x was equal to. If you do the partial with respect to x, then you would run across this along this direction, looking at the variations with t staying constant. All right, now I'm going to ask you to do this completely, and we'll look at our results together when we get back to class. But I ask you to recall what the field strength looks like for a conductor, a spherical conductor of radius capital R. So could you draw me E as a function of where you are, the radial value, and hopefully you can remember that. You need to remember that. If you feel weak on that, you could look it up in the book, but before you look it up in the book, see if you can do it without looking it up in the book. And then if you feel nervous about it, look it up in the book. And then once you have gotten E, I would like you to get what the potential looks like for a conductor again. And I would suggest that what you do is to look at this graph and say, what will I take the derivative of here, the partial derivative if you like, what would I take the derivative of here to get this function that you have up here? And let that instruct it. If you like, but I find this very hard to do, you could look at this graph and say, if I integrated this graph, if I added up the areas under this graph, what would this graph look like? And then come over here and again draw the field strength for an insulator. This would be a uniformly charged insulator with its charge going all the way into the center. What does the field look like for an insulator? And then what would you take the derivative of here to get this value? And this one, at least to my eyes, looks goofy, and I was very uncertain about it. I ended up making a spreadsheet and integrating that spreadsheet for the values of this function to see what I got here, and I did get it correct, but it was like they don't put it in the books. I don't know why they don't put it in the books, but I'm certain that what I have is correct. As certain as I ever am. And again, although I hope the last was not too frustrating, because I'm asking you to do it again without any feedback from me. This is a little bit easier. I give you the potential as a function of R. What is the graph that you get here? And by taking derivatives there. And again, what would you take the derivatives of here to get this? And consider constants of integration while you're doing this one here. Finally, we have a little nugget of conductor. This is a conductor, and it is a solid, and then I put it, and so it's full of atoms. It's got electrons and protons all through it. And then I put it in an electric field. It doesn't have to be neutral, by the way. I don't mind if this thing has charge on it. But I put it in an electric field. And remember that what these arrows mean for the electric field is that is the direction that a positive charge would be pushed, were a positive charge there, but a positive charge is there. And the negative charges would go opposite to the field arrows. And so this is a conductor. They can move, and when the field pushes them, they will move. They will rearrange. We call that an induction of charge, and they would rearrange until the negative charges had moved sufficiently to this side and leaving this side sufficiently positive that the field inside of the conductor is zero. We made this argument before, that the rearrangement is going to produce a field. Let me draw the field for you in red. The field drawn in the direction a positive would go like this, and so that is contrary to the field that's causing the rearrangement, and the net field here is going to be the superposition of those two fields. And so as long as there is a non-zero net field, their rearrangement will continue until the net field is zero, and then the rearrangings will stop, at which point the field inside, oops, I can't get rid of that red arrow. You wouldn't be too bothered if that red arrow stuck around. The field inside of this will be zero, which means if you go from any place inside of this to any other place inside of this, that you follow any path, you are going through a field whose strength is zero all along that path. And so the potential would be, well, it seems like the potential would be zero, but that's only if you call the potential at one point in this zero, then the potential at every other point would be zero. This could be at a potential, but it will be everywhere at the same potential. That this is really the change in potential I'm interested in here, and there will be no change in potential. That we say that what you have is an equipotential. A conductor will always be everywhere at the same potential. Going a little bit further, we can, and I hope my shaking things didn't cause this to no longer line up, close enough. At the surface, the field would have to be perpendicular. All of this charge will be on the very outside. We have Gauss to tell us that. So all this local charge will be on the very outmost skin, and the field will be perpendicular at the skin. Because if there was a component of the field parallel to the surface or tangent to the surface, then that would cause a rearrangement of charge. A rearrangement of charge which will continue until the result of that rearrangement, no, it's not going to go away. The result of that rearrangement is to make the field, the tangent component of the field, zero. So by the same argument again, we say that you cannot have any field tangent at the surface. It must all be perpendicular. That these were supposed to come around to being parallel again to the field, but here locally it would be deformed to be perpendicular to the surface. Thank you, and see you in class.